you notice something we don't need to know is what? Mass of the sun. Although annoyingly, I happen to remember it's 1.99 times 10 to the 30th kilograms. As I've mentioned with you before, I'd rather not remember that, but oh well. It's my curse. So 2/5 cancels. Oh, and 8 divided by 2 is 4. Anyway, we should do some calculating here. What do we got? So we have the radius of the sun, which we figured out was, whoa, 6.96, let's say, times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, times 10 to the 8th meters. Seems big. Is that right? Yeah, whatever. Let's see here. I'm not terribly worried about you guys collapsing any suns into neutron stars anytime soon, so if we make a mistake here, it's probably not going to hurt anyone. I worry more about the engineers. They build stuff you use. 4 divided by 2, 8 divided by 2. You guys engineers? Okay, just checking. 8 divided by 2 is 4, raised to the sun squared. Okay, divided by 12 times 10 to the 3rd meters squared. What do we get? This all just multiplies omega naught. We'd really just like to find the factor by which it speeds up omega naught, right? So what is that? Stupid logarithm. All right, come on. Whoa. Great. Googly moogly. Whoa. That's big. 1.24 times 10 to the 10th. Did you guys get that? Times the initial omega naught. That's fast, right? So you see, now, what would happen if we said that the lost mass carries off angular momentum, right? Then you would only get what? You'd only get to keep 25% of the original angular momentum. So I think you would, essentially, if for part B, you would just take this and divide by, well, this times 0.25. Well, oh, no, other way around. 0.25 of the initial angular momentum would be equal to the final angular momentum if 75 of if the lost mass carries off its angular momentum with it. You'd only have 25% of the initial angular momentum before the mass is lost in the end, right? I worry about that number. Just a second. Oh, this is number 90. We're stuck. It's right then. No, I don't think it's wrong, but this illustrates something, right? Is that if a star is turning even a little bit, right? If it collapses down, the process of angular momentum being conserved forces that star to spin faster and faster and faster and faster as it collapses. This is one of the things that maintains the stability of stars, is just its spinning, because it doesn't want to spin that fast. When things spin that fast, they tend to fly off, right? If at some point it spins so fast, it won't stay stuck together, right? If you've watched the right YouTube videos, you can see people, if you spin like CDs fast enough, what happens to them? They just fly apart, right? Anything pretty much, if you just stick it to something that will rotate really fast. If you rotate it fast enough, it just flies apart. And the same is true for stars. But what's a neutron star, by the way? What does that mean, neutron star? What's a star? What state of matter is a star, for the most part? It's like a big ball of fire, right? So what are the three states of matter that we're familiar with usually? Yeah, solid, gas, liquid. What's the fourth? Plasma. Where do you see plasma? Stars, but also fire, right? If you want to see plasma, start a fire. I mean, no, don't start fires. But, well, in a controlled environment, start fires. Or be a fireman. Anyway, but yes, fire is plasma. And a star is plasma. Why it's a plasma is that the electrons in the atoms are disassociated from their bond. They're not bonded to the atoms anymore, right? So like all of the electrons are free. And they're just shared amongst all of the nuclei in a plasma, something like that. So the electrons are no longer bound to atoms in a plasma. That's what makes a plasma different than a gas, a liquid, or a solid. Well, a neutron star is when all of the nuclei of all of the matter involved have just collapsed down together to make one giant, stupid nucleus. It's just a bunch of neutrons, one after the other, packed together. It's like a giant nucleus. That is insanely dense, all right? That's what leads to this radius, right? Now, that's interesting though, right? Because that's another kind of thing that you might find. And I think we have observed neutron stars. And in fact, the process of neutron stars collapsing, in the process of them collapsing, they would tend to make certain radiation that's signature of trying to, lose this energy of rotation. It can lead to what are called, if I remember right, I don't know, there's various scenarios that we talk about in astrophysics in terms of neutron stars, the birth of neutron stars, or the death of neutron stars. If you have a neutron star collapse into a black hole or something, then that can lead to like giant explosions in space that lead to these things called gamma ray bursts, which were big when I was in grad school. Although they soon became replaced with these things called type 1a supernova. But anyway, we're always looking for new kinds of stories to tell in astrophysics which give us some sort of window into distant things. Because the physics of these processes, in principle, should be somewhat standardized, and they give you some sense of how far away something is based on the intensity of what you see. Although from what Dr. Buderez was telling me, there's some recent news that suggests that we had this idea that type 1a supernovas were like uniform. Apparently they're not, if we believe a paper that's recently written. So then that casts doubt on their view of the acceleration rate of the expansion of the universe. I don't know. All I'm trying to tell you guys, when you watch science news about astrophysics, you should remember that it's much like the testimony from a person you see in like one of those Dateline specials where they keep coming back to the person and they keep updating their testimony and like it keeps changing. It's a lot like that. Like if you give them a decade, they'll change their story. And I think they're after the truth, but they put far too much stock in current arguments a lot of times. So you have to take it with a grain of salt, what people say in astrophysics. This kind of stuff, on the other hand, well, this kind of stuff, I mean, it's harder to get this wrong, right? Uh-oh. Why are you still here? Leave. Go. Go away.